Efficiencies and Combustion Symposium. Our next speaker for the evening is Jinhoon Choe from Dr. Sun's group, and he will be speaking about plasma-assisted flame stabilization in a swirling flow.
Yeah, hi. So, good afternoon, everyone. My name is Jinhoon Choe, working with Dr. Sun. So today I'd like to present plasma-assisted flame stabilization in a swirling flow. So here is my outline. So let's move on to the introduction. So before I came to Georgia Tech, I worked 7 years in the Doosan Heavy Industry, which is Korean company. And we developed 5 megawatt class gas turbine engine for electricity. So left picture is 3D modeling, and right picture is the first manufactured engine. So I was in charge of developing the combustors. So most gas turbine combustor employ the dump combustor with the swirling flow like this to stabilize premix flame. So so this figure is typical flow field of annular swirling flow. So it has 2 recirculation regions. So A is outer recirculation zone due to a sudden expansion of dump combustor, and B is inner recirculation zone due to vortex breakdown. So flame in the swirling flow can be stabilized at 3 locations. So number 1, inner shell layer, which divides inner recirculation zone and annular jet, and number 2, outer shell layer, which divides outer recirculation zone and annular jet, and also number 3, vortex breakdown bubble. So to enhance combustion or control the flame activity, nanosecond pulse plasma was used. So Lacoste et al. Used the nanosecond pulse plasma, and he found that combustion instability reduced by the plasma. So I used the same burner and focused on the flame stabilization. So this is my experimental setup. Air and methane were mixed in the mixing chamber and fed through the swirler. Also, plasma discharges between the center electrode and outer rim of the injector tube using the plasma generator. So this photo is direct photo of plasma discharges, and the below graph is waveform of current and voltage. So let's move on to the resultant discussion. This map is a flame stability diagram as a function of equivalent ratio and airflow rate. So inner shell layer flame was observed above the black line, as shown in A and B. And then when the equivalent ratio decreased to the B, oscillating flame were observed. And at these conditions, inner shell layer and outer shell layer flame was also observed, as shown in B and E. And then if I decrease the equivalent ratio further, then from B to C, then flames blown up at C point. However, in the zone B, flame if I decrease the equilibrium ratio from E to F, then flame can transit to the vortex breakdown bubble flame, as shown in F. So, strangely, I can ignite the flame at the point C. So there exists a vortex breakdown bubble flame at point C, and then after ignition of the flame, if I increase the equilibrium ratio to the purple line, then flame extinguish again. So that means that there is a gap between the blue line and purple line where the no flame exists. With the activation of plasma, there is always stable inertial ray flame exists. And we also investigate the lean-blowoff limit, so above the lean-blowoff limit, and we also investigate the lean-blowoff limit by varying the peak voltage and repetition frequency. So the result shows that peak voltage is a dominant factor to extend the lean-blowoff limit rather than the pulse frequency. And also, I studied the impact of nanosecond pulse plasma on flame dynamics. So I observed the flame at point G and H using the high-speed camera. And the right graph shows the maximum intensity of each left photo over the time. So flame shows bright and dark, and bright and dark, with a duty cycle of 0.3 seconds. And for each point, flames become dark and bright and dark with a duty cycle of 0.9 seconds. So with the activation of the plasma, it shows that the flame stabilized at the inner shell flame region. Okay. And then to study the effects of nanosecond pulse plasma on NOx and CO emissions, I also measured the exhaust gas at the exit of the cross tube. So when you see the left graph, hollow one is with the plasma, and solid one is without the plasma. So plasma reduces CO dramatically, however, increase the NOx emissions. So to further investigate the reason of the increasement of NOx emission, we also measured the NOx emission from the zero equilibrium ratio to the 0.8. So it shows that so this graph shows NOx emission was normalized by the plasma power, and it shows that NOx emission increased through the 3 stages. So first one is air plasma without any pure addition, and small amount of pure addition, and then intense flame. And then I increased the voltage and decreased the frequency under the same power. So it shows that NOx has increased at the higher voltage, which means that NOx emission is mainly governed by the peak voltage rather than the pulse frequency. And then finally, to study impact of nanosecond pulse plasma on combustion instability, I also measured the pressure fluctuation at the exit of the quartz tube. So at these conditions, there is a self-sustained combustion instability with a high level, and there is a pulse peak near the 237 hertz. So at 5 kilovolts, when I increase the frequency of the plasma, then there's no reduction of combustion instabilities. However, at 15 kilovolts, when I increase the pulse frequency, it shows that as I increase the frequency of the plasma power, the pulse peak and the amplitude of pulse peak decrease. So this result also shows that peak voltage is a main parameter to reduce the combustion instabilities. So here is my conclusion. So when the plasma was activated at the exit of the injection tube, first I found that the dependence of flame transition on flame history disappeared, and lean-blowoff limit could be significantly extended, and stable inertial layer flame attached to the center body at any condition before blow-off. And also plasma can improve the combustion efficiency as decrease of CO concentration, but could increase NOx emission at the same time. The effect on extension of lean-blowoff limit and NOx emission and reduction of combustion instability from peak discharge voltage was found to be more dominant than pulse frequency. So I need further investigation and optimization on plasma properties, and also minimize the NOx emission and maximize the effects of plasma on blow-off limit. So that's all my presentation. Any questions about? Yeah.
Why do you think using the plasma increases the NOx emission?
So, yeah, I think there's two possibilities. First thing is small amount of of methane molecules plays an important role, and also in this area there's a high temperatures in the plasma discharges, so that increase the NOx emission. But my result is contrary to the other research, because many researchers report that there's a lots of good result like this, but they found that NOx emission is not increased dramatically. So, yeah.
Question. How much of that change do you think is due to changes in the flame shape and the way like the whole combustion process is changing, and how much of that do you think is due to the effect of there being plasma present? So do you think that's generated by the presence of a plasma at some point, or by the global flame shape changing?
So due to the plasma, there's a lots of radicals are generated here, and I think that is holding mechanism for the flame.
Right.
But yeah, I need further investigation about that thing. So I just observe it, and what I need to do is analyze and to understand more. So Actually, I don't know exactly, not yet, yeah. Yeah,
What is the practical application of this? Are you eventually going to stabilize a flame using this high-frequent discharge? Is that a reasonable thing to do? Or is there another reason why you're doing this? And just understanding is a good reason.
okay, so many researchers doing these things to decrease combustion instability, but also this, so I call that this thing is dynamic flame stabilization, and the flame shape is also important. So, for example, due to some environment, there's a lit flame, then I can apply the plasma actively and attach it to the flame using the plasma. So, for the safety reason, in the gas turbine, there should be the stable flame, and these flames are very unstable. So using the plasma and temporarily apply the plasma, then I can shift this flame to the inertial flame. So that is benefit of my research.
But temporarily.
Yeah.
So this is like an emergency, in case of blow-off, light plasma type situation. I guess, if the flame blows off, you light the plasma torch and you're back to nominally stable operation. Is that the idea?
Yeah, so the future goal is plasma has lots of benefits. So future goal is using with apply the plasma and flame, we can get some benefits from it. But in this point, I think that is temporary solution for that.
Would it make sense to plot, instead of plotting against kilovolt and frequency,
Yeah.
looking at the amount of energy that's being put in per second or some other form of energy? Because I'm not sure it's the voltage that's doing it, 5 kilovolt versus 15 kilovolt, but you're depositing a different amount of energy. And maybe plotting an energy, I don't know whether that would shed some more light on.
Right. So, yeah, I have a current graph and
Yeah.
voltage graph, so I can integrate it
Right.
and get. And also, this is a one pulse, so I know the frequency. So integrate this thing and multiply the frequency, then I can get the energy.
Yeah, and then
Yeah,
plot
yeah.
energy against.
Yeah, that is
I don't know. maybe
yeah
that
good
would-
suggestion. Yeah, I also do that.
Any questions? Where's up?
Just a quick one. How do you think your changing the type of plasma generation would impact your conclusions if you, for example, used microwaves to generate plasma? Would it have different impact, you think, or it is dependent to the way that you generate the plasma?
Yeah, so what I use is nanosecond pulse plasma, and other people use a microwave or microsecond pulse plasma. So yeah, that is also a good point. I can use other kinds of plasma and see the NOx emission and compared to these things. Yeah.
Any questions? Okay, let's thank our speaker.
Yeah. Thank you.